faculty member of the UP School of Statistics and the awardee of the 2022 University of the Philippines Statistical Center Research Foundation Incorporated Professorial Chair in Statistics. He obtained his BS Statistics degree from UP Diliman in 2010 and graduated magna cum laude. He received his PhD in Statistics degree from the University of Maryland, the UP School of Baltimore County, with a dissertation entitled Rectangular Statistical Regions with Application in Laboratory Medicine and Calibration, under the supervision of Dr. Thomas Matthew. This work earned him the 2020 Outstanding Graduate Research in Statistics at UMBC. He also worked as a research fellow at the U.S. Food and Drug Administration and as a lecturer at UMBC. Our speaker received numerous research awards, including the 2021 American Statistical Association, ASA, Biopharmaceutical Section Scholarship Award for Notable Research, Academic Achievement, and Applied Project Work related to biopharmaceutical statistics, and third place in the poster competition of the 2020 ASA Biopharmaceutical Section Regulatory Industry Statistics Workshop. He has written numerous refereed journal articles and is a recipient of various university and department awards, including the One UP Faculty Grant Award for 2016 to 2018. He is currently a member of the American Statistical Association, Institute of Mathematical Statistics, International Statistical Institute, Society of Industrial and Applied Mathematics, and the Philippine Statistical Association, among others. Everyone, let us all welcome Dr. Michael Daniel Lucagbo. Sir Mike.
Thank you, Lian, and good afternoon, everybody. Thank you all for coming today. First of all, I'd like to thank the Office for Research for organizing this talk, this professorial chair talk. The Office for Research is headed by the very capable Dr. Imogen Evidente. Thank you very much. And welcome, everybody. To my talk, I'll be talking about dissolution profile comparison. So let me start by sharing my slides. I hope everybody can see that now. The title of my talk is In Vitro Dissolution Profile Comparison. I will explain what that means in a bit. So first of all, drug absorption is the process of a drug moving from the site of administration or the site of entry into the body into the bloodstream. And drug absorption from a solid dosage, such as a tablet or a capsule after oral intake, depends largely actually on the dissolution of a drug. Right? It doesn't just depend on dissolution. There are other factors that it would depend on, such as the release of the drug and also the permeability of the gastrointestinal tract. But it largely depends. So it's highly influenced by the dissolution itself of the drug. And so that's what we are trying to investigate in my particular study. And it has been shown that in vivo, in predicting in vivo performance, meaning performance of a drug inside the living organism, is actually highly correlated with in vitro, meaning outside the living organisms, say in a test tube or some particular medium outside the organism. Those two performance of a drug under those two particular media are highly correlated, and that's why in vitro dissolution tests, which are less costly than in vivo tests, are a standard acceptable practice already by the US FDA. And here's how US Pharmacopoeia explains dissolution testing. It measures the extent and rate of solution formation from a dosage form, such as tablet, capsule, ointment, etc. And we will be comparing these dissolution profiles for reference and test products. And my talk, essentially, it's a statistics talk. I'll be showing the methodology that I'm developing for that. But this is the main application, really, to compare dissolution profiles of reference and test products. Now, like I said, there is a very high correlation between in vitro dissolution profiles and drug absorption, in vivo drug absorption. And as long as we are maintaining the physiological conditions And as long as also we are maintaining the set of dissolution time points, then we can be confident that there is a high correlation. And so the FDA guidance explains that in vitro dissolution tests are used for a variety of purposes. No, not just in comparing reference and test products. Yung number 2 dyan, that's what what I'm referring to by comparison of new and existing products, but it's also used in comparing lot-to-lot quality of a drug product. There might be differences in types of equipment across different batches. The drug products may have been produced with different equipment or slight differences in quality. How do you assure bioequivalence between those types of drugs from different batches? And it also ensures continuing product quality. Halimbawa, kung ikaw ay isang kumpanya, and then you open up a new branch or you scale up, you open up a new branch or a new office, a new site elsewhere, you still have to show that the drug products that are produced in that new branch are bioequivalent to the original branch or the original site. So in vitro dissolution tests become very useful in that respect. And also, I'm also saying here that comparable in vitro dissolution data is part of requirements for approval of ANDA, abbreviated new drug applications. Typically, this apply to new generic drugs that you will show its bioequivalence with existing drugs. So in vitro dissolution comparison would be very useful there. Now, here are examples of dissolution profiles. Now, the data that this plot here, the data source is from this paper by Jong et al., written in 1997. So this is actual data, and we have here on the x-axis the dissolution time points, and on the y-axis the percentage of the drug that is dissolved. So apparently this is a controlled release, kasi masyadong matagal bago ma-dissolve. And we have here the values, percentages across time, and as we can expect, it is increasing, the increasing amount of the drug that's dissolved. And we are comparing yung reference or originator kind of drug versus a test or a new kind of drug in terms of dissolution profiles. And it's really these two that we are comparing here, the blue and the orange ones. And how do you say that they are similar? How do you say that they are equivalent to each other? And we have to have a precise definition for that. And can we test if we have significant evidence that they are really equivalent to each other? So that's basically the problem that I'm trying to address here, equivalence between profiles. And here's another example, lots of examples out there. This is an example from Chi et al. In 2019. So I'd like to draw your attention just to the graphs on the right part. These are profiles for paracetamol and chlorzoxazone. And these profiles are corresponding to different dissolution media. No, magkakaiba sila ng pH levels dyan. No, water has pH level of 7, right? And other various pH levels. Also, we look into amount of drug dissolved as a function of those pH levels, and also just comparing these two, paracetamol and chlorzoxazone. How do you declare that the profiles are equivalent to each other? So it's not quite straightforward to answer that. There's lots of methods that have been proposed to establish equivalence or similarity between those dissolution profiles. Here are some examples. I'll just run through them. One example of a way to measure dissolution profile similarity is this weighted mean square difference. No? So some weights are chosen there, Wj. Pwedeng yung equal weights lang, magiging 1/p yan. And we take the square difference between the mu rj dyan ay the mean for the reference product of the particular time point j. So minus mu tj, mean for the test product of the particular dissolution time point j. We take the average square difference between those means. If we choose equal weights for WJ. But in general, we get the sum weighted sum there of the square difference between those means. Yung number 2 naman is weighted absolute difference. Instead of getting the square, why not just get the absolute value? And then there's also what's known as the Resigno index. I decided not to show the formula. It's a bit complicated. And besides, we're not going to need that. But these are some of the ways to assess the solution profile similarity. So lots of metrics have been put forward. And meron ding difference factor. I think these two, difference and similarity factor, are more popular than the other ones. And both were proposed by Moore and Flanner. So yung F1 dyan is known as the difference factor. The reason why it's known as a difference factor is that the larger the value of F1, the more different they are. Now, F1 larger, or the more dissimilar they are. And then yung similarity factor naman is the opposite. The larger the value of F2 is actually indicative of similarity between reference and test dissolution profiles. And F2 is what I will be focusing on today, kasi it's really the one that's recommended by the US FDA. And it's also, you will recognize that it's really an unknown parameter because it's a function of unknown parameters mu rj and mu tj. Both of those are population means. So F2 is some parameter, and its structure looks very complicated. But it was chosen to be of that form. If you're wondering bakit ganyan yung formula niya, the idea is just to make it range from 0 to 100, where F2 value of 100 means that the profiles are identical to each other, and F2 value of 0 means that they are totally different from each other. Makikita niyo naman dyan, no, na F2 equals, if you substitute, if you have mu rj minus mu to j, just imagine that those pairs of means are always equal to each other, so that that square difference just becomes 0. Then F2 indeed becomes equal to 100. So a 100 value of F2 means that the profiles are identical to each other. And F2 ranges from 0 to 100. Now, which value there do we choose as a cutoff? Now, that above this one, we consider the profiles to be sufficiently similar. The commonly chosen cutoff is actually 50, no? Yung nasa gitna. And that corresponds to an average square difference of 10%. So these are percentage of the drug that's dissolved. An average difference of 10% at all measured time points results in F2 value of 50, and F2 values greater than 50 indicate similarity of dissolution profiles. And my task here is to propose a formal statistical test. Now, given that you have your data, given you have your dissolution batches, given that you have your reference and test drug dissolution profiles, how do you test if F2 is significantly greater than 50? Or do we have sufficient evidence that F2 is greater than 50? F2 here is some parameter, but the problem here is that, again, F2 has a very complicated structure. But if you look closely, F2 only depends on 1 over p summation of mu rj minus mu tj squared. It only depends on this part. So I can take this particular parameter actually, and I will be calling it my delta here. And then I can reformulate my hypothesis testing in terms of delta. And actually, F2 equal to 50, now you can verify that easily, that F2 equals 50 corresponds to a delta value equal to 99. And delta values greater than 99 indicate that they are dissimilar, and delta values less than 99 indicate that they are similar. So the first set of hypotheses there is really equivalent to the second one. I can express my hypothesis in terms of delta. And that's what I will be doing for the rest of this talk. Now, I will really be addressing this problem. How do we test HO, delta greater than or equal to 99, against the alternative hypothesis, delta less than 99? And delta here, therefore, is considered my parameter of interest. Now, to answer this problem, I will be using a multivariate normal setting, multivariate normal framework, which is a typical assumption in dissolution test profile comparison. And I will be using also fiducial inference because there seems to be a logical, there seems to be an available solution based on the framework that we will be assuming, parametric framework. Now, fiducial inference is one of those types of inferences, not just like frequentist and Bayesian, introduced by R.A. Fisher in the 1930s. It's been there for a long time, but it has largely fell into disfavor in mainstream statistics. Medyo nagkaroon dyan yung as Hanig there. Hanig is really the person who has most recently worked on the foundations on fiducial inference, and he's a modern researcher. He reports that fiducial inference experienced a bumpy ride during its early years and eventually fell into disfavor in mainstream statistics. I think that's a pretty fair assessment. Now, if you, even in standard textbooks by like Casella and Berger, that book does mention fiducial inference, pero kung babasahin mo yung book, it seems like it's not very favorable. Yung sinabi doon about fiducial inference, and you cannot really blame that book. That book was written into, it's still a great book. It was written, I think somewhere, its second edition was somewhere in 2002. And a lot of the emerging research in fiducial inference happened after 2002. So fiducial inference has recently made a comeback, although it has made a comeback under different names, like generalized inference and also confidence distributions. Like papers by Jan Hanig and Sam Weerahandy really have catapulted itong fiducial inference back into mainstream statistics. And once again, it's once again a very useful tool. And if you read also a modern classic by Bradley Efron, the book Computer Age Statistical Inference, if you read about fiducial inference, now, kung babasahin mo na siya, mas maganda na yung discussion doon. I think it's a better assessment of fiducial inference already. Okay, so what does fiducial inference do? It obtains a measure on the parameter space without assuming a prior distribution. So it borrows from an idea from Bayesian inference, in that we want to form a distribution around a parameter, but we don't assume a prior distribution. We don't run into that burden. And in order to do that, the randomness is transferred. It's shifted from the model, from the likelihood function, the randomness is shifted to the parameter space. And now we will show how exactly we are going to be doing that. We will be doing, one particular type of fiducial inference is itong generalized confidence intervals. And I will be outlining the discussion on generalized CIs from the book of Krishnamurthy and Matthew. So let X be a random sample from the distribution. So that vector X there contains n observations. It's a random sample taken from this distribution where theta is a scalar parameter of interest. So delta there is some parameter. We're not directly interested in that. We call that a nuisance parameter. We're particularly interested in making inferences about theta. And let small x be the observed sample from the data. What's known as a generalized confidence interval for theta? Remember that theta here is our parameter of interest. It's computed by taking percentiles of a GPQ, of a generalized pivotal quantity. So we define itong GPQ, yung big G dyan. G is a function of big X, small x, and theta. Small x there denotes the observed sample, and big X there denotes the distribution of the random sample. It's a random vector there that represents a distribution of our random sample. And since G is a function of big X, G is also a random quantity. Function of big X, small x, and theta, it could also be a function of the nuisance parameter delta. And in particular, G satisfies those two conditions here in order for it to be a valid pivotal quantity, a valid GPQ. Its distribution should be free of all unknown parameters. And that's what we would be assuming of typical pivotal quantities, right? A distribution is free of all unknown parameters. Now, G itself can be a function of unknown parameters. So it can be a function of theta and delta, but its distribution is not a function of unknown parameters. And moreover, if you substitute the observed sample into big X, no, yung big X dyan, papalitan mo rin ng small x, you will get back the parameter of interest theta. So those are the two conditions that we require for G in order for it to be a generalized pivotal quantity. And we make use of this in this talk, generalized pivotal quantity, or we can just call it fiducial quantity. Now, if you want to do a confidence interval for theta, remember that G is a GPQ for theta. G would be very useful there in finding the confidence interval, because all you need to do is to take the quantiles of G. Remember that G is random, because a big X there is random. If you just take the quantiles of G, the alpha over 2, and 1 minus alpha over 2 quantiles of that random variable G, then those two quantiles taken together would form the 1 minus alpha 100% confidence interval for theta. And that's a two-sided interval. We can also do one-sided intervals. And we take this approach in this study. We will be forming a upper-sided interval, and we use that in our decision rule for our hypothesis test. Okay, now there are two theorems that I will be using with. In particular, itong una, no, will be very useful in deriving our fiducial quantities for any n by n positive definite matrix A. There exists a unique upper triangular matrix T with positive diagonal elements such that A equals T prime T. So this decomposition is unique, and it's known as the Cholesky decomposition. T here is an upper triangular matrix. In other words, T prime becomes lower triangular, and the diagonal elements has to be positive. So such a decomposition exists and is unique for any positive definite matrix A. And this result will actually be very useful to us. And then the second theorem here is relating to Wishart random variables or random matrices. If you have Z alpha, that's IID normal with mean 0 and covariance matrix sigma, where sigma is positive definite. And if you form A to be that way, sum of Z alpha prime, where Z alphas are IID normal, then A is actually a Wishart matrix. But based on that construction, A is positive definite with probability 1 if and only if n is greater than or equal to P. If and only if our sample size is greater than or equal to our dimension. Or the degrees of freedom there is greater than or equal to the dimension. That is our condition, and then we have A that's positive definite with probability 1. So these two theorems would be useful in development of our methodology. In particular, yung positive definiteness na property dyan in the second theorem there would make it eligible to have a Cholesky decomposition. Okay, so here again is our setup. Those are our observations taken from test product and reference product. And mu T and mu R are our mean dissolution profiles. And we compare mu T and mu R based still on our F2, equivalently based on the parameter delta that I explained earlier. There have been approaches to do inferences about F2, like the paper by Islam and Begum, where they used bias-corrected and accelerated bootstrap. Kaya lang yung sa approach na, they're doing actually a two-sided interval. What is important for us is a one-sided inference because we are testing a strict inequality. We have a one-sided test here. So what is of interest for me is a one-sided upper interval. And moreover, there's really no assessment here about the coverage probability in their paper or the power of the test. So we do this in this setting again, a multivariate normal setting where mu t and sigma t are the parameters, unknown parameters for the test product, and mu r and sigma r are the unknown parameters for the reference product. And our task here is to find fiducial expressions for mu t, mu r, sigma t, and sigma r. Once we find those fiducial expressions, then we can actually get the fiducial expression also for delta. And that fiducial expression for delta, we take the quantile of that fiducial expression, and that gives us a way of stating a decision rule for our problem. Okay, so first of all, since sigma t and sigma r are positive definite matrices, we have Cholesky decompositions for them. Now, where gamma t is the lower triangular Cholesky factor for sigma t, gamma r is lower triangular Cholesky factor for sigma r. Again, we assume that sigma t and sigma r are positive definite matrices. Yung ST tsaka SR din, they follow Wishart distributions. And as long as the degrees of freedom is greater than or equal to the dimension, then they are also positive definite with probability 1. And they also therefore have Cholesky decompositions like that. And we call VT, VT is my notation for the lower triangular Cholesky factor for ST, and VR is the same for SR. So these decompositions will be useful to us in a bit. Once again, here are the distributions of our summary statistics. ST and SR are both Wishart. And the covariance matrices there are 1 over NT minus 1 sigma T and 1 over NR minus 1 sigma R. X bar T and X bar R are both multivariate normal. And from these distributions of our summary statistics and also our sufficient statistics, we can formulate our fiducial quantities. Now, if we rewrite this Wishart distribution, ST follows Wishart, and therefore, from this characterization of Wishart, ST can also be written as summation of YT alpha prime, where YT alpha has this multivariate normal with mean 0 and variance 1 over NT minus 1 sigma T. So that follows from this fact, ST has a Wishart with this covariance matrix. So this characterization can also be written in terms of yung YT alpha has the same distribution as 1 over square root of NT minus 1 gamma T ZT alpha, where gamma T, remember, was the Cholesky factor of sigma T. Okay, and ZT alpha here is normal with mean 0 and variance identity. So this, in the second line here, the expression in parentheses, its distribution is normal with mean 0 and variance 1 over NT minus 1 sigma T. So same as the distribution of YT alpha, and then sa kabila dyan is just its transpose. We can rewrite this as in this third line here, where we've factored out yung 1 over root n minus 1 gamma T. And what's inside here is another Wishart matrix, where ZT alpha now is normal with mean 0 and variance identity. And I call that Wishart matrix HT. So this HT is Wishart, its degrees of freedom is now NT minus 1, and covariance matrix identity. Since it's Wishart again, as long as NT minus 1 is greater than or equal to P, then it is positive definite with probability 1, and I can form a Cholesky factor for that. And I do the same for HR corresponding to the reference product. The derivations here for ST are just for the test product. I do the same for the reference product, and I get those factorizations for HT and HR, where BT and BR are the Cholesky factors for HT and HR respectively, and BT are lower triangular. Okay, so given this, this imply that VT has this particular distribution. So remember that VT was the Cholesky factor for ST. So balik tayo dun sa kanina. We had this. And since the Cholesky decomposition is unique, then I can actually equate that with, if I substitute here, yung HT is, if I substitute there yung BT prime, then I can equate this to, and remember that gamma T was the parameter of interest there. And so I could reverse this part. I could rewrite this such that gamma T is left on one side of the equation, and that gives me actually my fiducial quantity for gamma T, yung gamma T tilde dyan. So nagre-write lang ako dyan. And I'm also writing V sub T slightly differently now. I'm writing it, I'm italicizing it, indicating that that's already for the specific value. Kung baga yan na yung small x dun sa GPQ ko, that's already for the specific value of the Cholesky factor of my covariance matrix. And BT inverse, remember, was just obtained from the Wishart matrix. And I do the same for gamma R tilde here. So these are my fiducial quantities for gamma T and gamma R. And consequently, I can get a fiducial quantity for my covariance matrices. Now, how about the means? We go back to the distribution of x bar T and x bar R. No, they're both multivariate normal. And so we can characterize their distributions this way. That's a characterization where, again, gamma T here and gamma R are the Cholesky factors. I put a distribution around the parameter space. So you mu T tilde now, isolating mu T tilde, we can get these two equations below. Now, where I am already substituting the observed value of x bar T there. Instead of big x bar, small x bar na lang yan. And then I'm also substituting gamma tilde instead of gamma T. So gamma T tilde was the fiducial quantity for gamma T. And overall here, I have my fiducial quantity for mu tilde. Okay. So that gives me now the ingredients of in order for me to have a fiducial quantity for that delta expression earlier. All right, so here again is the hypothesis that I want to test. Now, HO delta less than or equal to 99 versus the alternative delta, HO delta greater than or equal to 99 versus the alternative that delta is less than 99. So I now have a procedure given that I have these expressions for my GPQs. I compute first the summary statistics. As usual, compute the summary statistics. So all of my inferences here are based on sufficient statistics because those are the sufficient statistics for multivariate normal. And then I compute the Cholesky factors for my covariance matrices. And then I take this random draws, yung UT, UR, and HT and HR. Those are random matrices. And then I use those when I compute this fiducial quantities. Now, using those formulas earlier for mu T tilde, mu R tilde, and the gamma tildes. And then from these fiducial quantities, now if I write the elements of mu T tilde and mu R tilde this way, in vector form, kung ganyan yung mga elements nila dyan sa step 5, then using those elements, I can form my delta tilde, which is the fiducial quantity again of delta. Now, you may wonder, anong gamit ng gamma dyan, gamma tilde, gamma R tilde, they don't even appear in step 5. Well, remember that in computing mu T tilde and mu R tilde, I used these gamma tildes. So they have to be computed first because their values will be substituted in here to get fiducial quantities for mu T and mu R. And this steps 3, 4, and 5 will be done over and over again. Will be done in as many times as you are needing fiducial quantities. And I am actually using 1,000 fiducial quantities in my simulations. So I have 1,000 values of delta tilde. Get the 1 minus alpha quantile or 1 minus alpha 100 percentile of those values. I call those delta tilde 1 minus alpha. And that gives me now my decision rule. Reject HO if delta tilde 1 minus alpha is less than 99. So that's the procedure for the statistical test. And it's really heavily based on our distributions for our parameter spaces. Okay. For simulations, to evaluate how good does that particular procedure perform, we have to compute the type 1 error rate. And when you're doing type 1 error rate simulations, all of your parameters have to be in the boundary of the null hypothesis. Its probability of rejecting HO given HO is true. So to ensure that the null hypothesis is correct, we do it in the boundary. And the boundary there states that the delta value is equal to 99. So we pick delta equal to square root of 99 here. This is small delta, not the big one. We pick small delta here equal to the square root of 99. And that implies that yung big delta value is actually precisely equal to 99. So itong setting 1 is no mean structure, meaning yung mu sub t dyan, there's no particular structure there except that it's increasing in time. But there's no particular linear or quadratic factor, no such structure is assumed. And setting 2 also, as the mean of reference and test profiles is often been modeled as a Weibull. So we assume a certain Weibull structure for the reference product. And then we just get this constant difference expression for the test product. So these two particular settings, so ganyan yung Weibull structure natin, merong parameters alpha r and beta r, and t is just the dissolution time points. I take alpha r to be 0.549 and beta r to be 0.521. And again, in order for this to have a value under the null hypothesis, I take delta to be the square root of 99. That implies that big delta is exactly equal to 99. So the values of sigma r and sigma t that I will be using are taken from the Zhong et al. 1997 dataset. And also the same ones are used in this paper by Jai in 2016. So I'm not showing it here, but these are 7x7 matrices, yung sigma r and sigma t. They were calculated from those two papers there that I mentioned. So that's for the simulations for type 1 error rate. And I use these various sample sizes for the test and the reference product. Each simulation setting is replicated 2,000 times. In order for me to have an accurate estimate of the type 1 error rate, I do it 2,000 times. And each replication, I make use of 1,000 fiducial quantities. And I take the 95th quantile of delta tilde across those 1,000 fiducial quantities. And here are the results. Well, so far, it seems to have difficulty with small sample sizes, and the ideal type 1 error rate is, of course, 0.05. It would have been nice if it would perform well when the sample size is small, because 12 is really the minimum sample size required by the scale-up post-approval change guidance of the FDA. But we are seeing here na 0.012, medyo mababa. So the test is still conservative when the sample size is small. And there seems to be evidence that it improves as the sample sizes increase. These sample sizes are the same ones that were used in this paper by Jai et al. So these simulations are very limited, but at least there's some indication here that it can actually improve. The type 1 error rate goes closer to 0.05 as the sample size increases. And it's also very important to understand the property of a statistical test. How powerful is it? And when we evaluate the power of a test, I vary here the values of delta. And as the value of delta decreases, it means that I go further and further away from the null hypothesis and into the alternative hypothesis. And I would expect the power of the test to increase as delta decreases. And yes, indeed, that's happening here. I'm assuming that the test and reference products have the same sample size. So for a fixed sample size here, for any fixed particular column there, yes, it does increase, but it relies on relatively large sample sizes. Perhaps sample size of at least 24 here para magkaroon siya ng mataas na power. If we typically want powers to be at least 80%. So it starts off with low power, but then as delta decreases, the power increases. And I was hoping for better results than this, but at least it's reassuring for me that the test is in the correct direction. No, it's behaving as I would expect it would, depending on the value of delta and also depending on the value of the sample size. At least that it's in, at least it really is going to 100% as the sample size increases whenever you fix your delta. So kahit ano yung i-fix mo dyan, no, kahit sa row ka mag-fix, the power increases from left to right. And if you also fix columns, the power also increases. You can see there, no, which settings would give you power of at least 0.80, for instance. So at least it's reassuring for me that it's in the correct direction there. Right, so just as a recap for the talk, the methodology takes a stride towards a formal statistical test for similarity of dissolution profiles. Now, I haven't seen yet a formal test, although again, doesn't mean that there are no studies that are being done towards this direction. This is a very active area of research. So it's possible that as I speak right now, there are other methodologies that are being developed. And one of those methodologies I mentioned earlier, yung by Islam and Begum, but they were just using a two-sided confidence interval for that. And what's more important for me is a one-sided kind of hypothesis testing. We can perhaps refine the methodology to improve type 1 error rates. Now, maybe the use of other fiducial quantities would be useful here. And more simulations. Now, admittedly, the simulations at this point are quite limited for just limited values of P. In fact, we just took P equal to 7 here. There might be other structures of this sigma T and sigma R, and we can consider various lengths or various dimensions for our test profiles. And then there are data sets that are available for application, actually, and I found 2 data sets. Now, one from this paper by Jong et al. 1997 and another one from Buchanan 2009. So 2 data sets that we can apply this methodology to. And here are my references, just the ones that I cited in this talk. And that's it. No, thank you very much.
Ayan. So thank you very much po, Sir Mike, for that wonderful and informative talk. So bigyan po natin ng clap reacts. Okay, si Sir Mike. Thank you very much po. So the floor is now open for questions. If you have any questions, you may use the raise hand feature of Zoom or you may type your questions sa chat. Okay? Okay. Sige po. Sir Mike, question lang po. Are there any limitations in using the similarity factor for testing po, sir?
Well, none that I know of. The reason I'm using similarity factor is it's the one that's recommended by US FDA. Yeah, I'm not aware. I'm pretty sure there are some limitations there. No, I don't know as of the moment what the limitations are in terms of relevance, to really see if the dissolution test profiles are different from each other. Right, so that's my only basis for using the F2. It's because it's the one that's being recommended.
Okay po. Another question po. Does yung F2, sir, yung similarity factor, does it take into account the differences in dissolutions within the test and reference batches?
Okay, yung mu2 and mu-t and mu-r there are actually population means already. Okay, so we are taking the averages within, if you have a sample of size NT for the test product and sample size of NR for the reference, you take the average, and that average is taken as your estimate for the population means. So is your question about the variability of those? Is it affected by that?
Yes,
Well,
sir.
certainly the estimation of the mean is also affected by the variability, right, of your data set. But the method that we have done here, that we have proposed, already accounts for that variability, because we also have fiducial quantities for our covariance matrix. Yeah.
Hi, sir. Any questions from the audience? Okay. Okay, na-absorb pa po nila, sir, yung topic. Any questions po? You may use again your raise hand. You may use the raise hand feature of Zoom, or you may type your questions. Okay. Sir, I also have a question. Would it be possible po, sir, to construct yung tester in the Bayesian setting?
Well, no. So we would run into the same kinds of decision that we need to make. You have to assume a certain prior distribution for mu t. You have to assume a prior distribution for mu r, and also for your covariance matrices. But certainly, no, this is just multivariate normal, and we can think of a variety of prior distributions for those parameters. So yes, in fact, that's one of the directions that I would like to explore, then to do a Bayesian testing approach for this. Yeah.
Okay po, sir. Any questions pa po from the audience? Okay. Okay. Ito po, sir, may question po. How did you determine the setting for the simulations?
For the simulations for the power, yung una is just no mean structure, and the other was Weibull structure. Those are parallel to the paper by Shuyan Jai and Thomas Matthew. So we based it using the same simulation settings. So that's already published in Statistics in Medicine. The second there, in particular, yung Weibull structure for the population mean, that is really a very common model for mean dissolution profiles for both reference and test products. So dun nang galing yung settings namin for the type 1 error rate. And for the power of the test, I thought it was just convenient if you change yung delta. It's really there, the delta, it's the delta that matters there, because the parameter that you are testing for is really delta. So since naturally you can pick values of delta in the degrees of 10, so that's why I picked 90, 70, 90, 80, 70, and 60. Yeah.
Okay. Thank you very much, Sir Mike. Last question po. May any last questions? Okay, going once, going twice. Okay. Sige, so parang wala na po masyadong questions. Okay. Thank you po very much, Sir Mike, for answering all our questions and for that wonderful talk. Okay, so yan. So thank you very much po. Bigyan po ulit natin ng clap reacts si Sir Mike. Ayan. Thank you very much po. Okay, so to express our gratitude, so we want to award the Certificate of Appreciation. Okay. Ayan, hintay lang po natin. Okay, so the certificate reads, the University of the Philippines School of Statistics awards the Certificate of Appreciation to Dr. Michael Daniel C. Lucagbo for the excellent lecture on in vitro dissolution profile comparison as part of the UPSS Professorial Chair Lecture Series. Given this first day of December 2022 via Zoom, signed Dr. Imogen F. Evidente, Director for Research of the UP School of Statistics, and Dr. Joseph Ryan G. Nansangan, Dean of the UP School of Statistics. Thank you very much po, Sir Mike.
Thank you, everybody. Thank you, Lian.
Thank you po.
Thank you also, Jean. Yeah.
Okay, now for the participants naman po. Okay, so for the participants, electronic certificates of participation will be awarded to all attendees. So you must be present for 75% of the activity's duration to receive a certificate of participation. So the certificates will be sent to your registered email address within 3 working days. Okay, so palakpakan rin po natin yung sarili natin. And your feedback matters to us. So for any inquiries and feedback, you may direct it to statresearch.upd@up.edu.ph. Okay? And, okay, so you may, again, nakalagay po sa chat box, you may send your inquiries and feedback to statresearch.upd@up.edu.ph. So thank you everyone for attending this Stat Speaks event. So please stay posted for our future activities. You may subscribe to our statistics mailing list. So here is the UP School of Statistics mailing list. So if you want to be part, so please go to bit.ly/UP Stat mailing list. And you may also like our Facebook page at facebook.com/UPDstat. So thank you everyone for attending. And we would also like to thank those who are regularly attending our Stat Speaks event. So banggitin ko lang po yung mga pangalan nila. We have Marty Banyaga, Rene Alvi Oquendo, Brian Rafor, Kasparov Repredo, Maria Salvacion Pantino, Mary Ruth Velasco, Patrick Joseph Siciliano, Ethel Estanislao, Thessalonica Cabaliza, Jocelyn Ubas, Iana Michelle Garcia, and ayan, meron pa po ata. Okay, so yun lang po. So thank you very much for participating in Stat Speaks 2022. So best wishes to everyone in the new year. Thank you very much po.
Thank you. Bye-bye.
Thank you.